There are two boxes, a glass box containing $1,000 and a mystery box. You have a choice. Take only the mystery box or take both boxes. Of course, there's a catch. The amount of money in the mystery box is determined by a computer. The computer tries to predict what you'll do. If it predicts that you'll choose the mystery box, it places $1 million inside. And if it predicts that you'll choose both boxes, it leaves the box empty. You don't know what the computer predicted, so you don't know what's inside the mystery box, but there is one important thing you do know. You're almost certain that the computer's prediction about your choice will be correct. To be more specific, one of the earliest and certainly the most influential published formulations of the problem is due to Robert Nozick, who wrote, "Suppose a being in whose power to predict your choices you have enormous confidence. One might tell a science fiction story about a being from another planet with an advanced technology and science that you know to be friendly, etc. You know that this being has often correctly predicted your choices in the past and has never, so far as you know, made an incorrect prediction about your choices. And furthermore, you know that this being has often correctly predicted the choices of other people, many of whom are similar to you. All of this leads you to believe that almost certainly this being's predictions about your choice in the situation to be discussed will be correct. When the game begins, the computer makes its prediction. You don't get to see what it decided, but based on that prediction, it either places $1 million in the mystery box or leaves it empty. Now it's your turn. Do you take only the mystery box, or do you take both boxes? This is known as Newcomb's problem, and I recently came across the problem in a video by Veritasium where they mentioned that people are split fairly evenly between two groups. Those who would only choose the mystery box, the one-boxers, and those who would choose both boxes, the two-boxers. At first, I thought maybe the reason that these two groups disagreed was because they had different objectives. Maybe the two-boxers were trying to reduce the chances of ending up with nothing, while the one-boxers were trying to maximize expected reward. But as I started hearing the reasoning behind each group's choice, I realized that even when both groups had a common objective, to make the choice with the highest expected reward, they still disagreed about what the optimal choice was. How is it possible that people with the same objective and the same information are reaching completely different conclusions? Well, it turns out they have very different ideas of what the expected rewards are. One-boxers think that if they choose the mystery box, the expected reward is $1 million, and if they choose both boxes, the expected reward is $1,000. So, to them, the optimal choice is clearly to choose the mystery box. Two-boxers, on the other hand, think that if they choose both boxes, the expected reward is $1,000 more than if they only choose the mystery box, meaning to them, the optimal choice is clearly to choose both boxes. So, who's right? Well, let's start with something everyone agrees on, the law of total expectation. To simplify notation, I'll use MB for mystery box and BB for both boxes. Assuming it's well defined, what's the expected reward if I choose the mystery box? Well, there are two things that can happen. I either make $1 million or I make $0. And by the law of total expectation, this means that the expected reward is this. Similarly, assuming it's well defined, the expected reward if I choose both boxes is this. To see which expected reward is greater, we need to fill in these four probabilities. And this is where the typical one-boxer and two-boxer approaches start to diverge. A common one-boxer thought process goes something like this. If I pick the mystery box, there's a very high probability that the computer predicted I would do that, because the computer is very good at predicting my choice. This means that there's a very high probability that the mystery box is full. If I pick both boxes, again, there's a very high probability that the computer predicted I would do that, which means that there's a very high probability that the mystery box is empty. So, the one-boxer's view is that these probabilities are very close to 1. Meaning this expected reward is close to $1 million, and this expected reward is close to $1,000. This is why one-boxers conclude that taking only the mystery box is optimal. The key idea that makes this one-boxer logic work is that both of these conditional probabilities are assumed to be very close to 1. Two-boxers go about things a little differently. A common two-boxer thought process starts by making a 2x2 table of all the possible outcomes. Each row represents an action you can take, either choose the mystery box or choose both boxes, and each column represents the state of the mystery box, whether it's empty or full. Then, in each cell, you write down the reward you would receive in that scenario. Looking at this table, you notice something interesting. If the mystery box is full, someone who chooses both boxes receives $1,000 more than someone who only chooses the mystery box. And the same thing happens if the mystery box is empty. So, regardless of whether the mystery box is empty or full, choosing both boxes always earns you $1,000 more. Why would anyone ever choose only the mystery box? Well, what if I told you that if you choose the mystery box, it's more likely that the mystery box is full, meaning you get $1 million. But if you choose both boxes, it's more likely that the mystery box is empty, meaning you only get $1,000. Well, you'd probably think that that doesn't make any sense. The computer already made its prediction, and it already decided whether to put the $1 million in the mystery box or not. Whether the mystery box is empty or full does not depend on what you do next. It already happened. And you know what? That's a perfectly reasonable objection. And inside that objection is the key two-boxer assumption. That the probability that the mystery box is full if you choose both boxes is equal to the probability that it's full if you only choose the mystery box. We'll call this probability P. P could be 0, 1, or some other value in between. Now, if we go back to our expected rewards calculation and plug in this assumption, it's easy to show that regardless of the value of P, choosing both boxes has a higher expected reward. And this is why two boxers conclude that choosing both boxes is the optimal strategy. So, why are one boxers and two boxers reaching different conclusions? Because they're starting from different assumptions. One boxers assume that these two conditional probabilities are very close to 1, while two boxers assume that these two probabilities are the same. Now, of course, people may be one boxers or two boxers for other reasons, so keep in mind that these assumptions are not the only assumptions one boxers and two boxers make. But if we focus on these two set of assumptions for a moment, it's actually not hard to see that these assumptions cannot both be true. If the one boxer assumption is true, for example, then this probability has to be close to 1. And if the two boxer assumption is also true, that means P has to be close to 1. But if P is close to 1, then this probability must be close to 1, meaning this probability would be close to 0, and that directly contradicts the one boxer assumption that it's close to 1. So both assumptions cannot be true at the same time. It's one or the other. But whose assumption is correct? Well, before we can answer that, we first need to define what we mean by correct. One natural definition would be to say that the correct assumption is the one that is mathematically implied by the problem statement. And if we use this definition of correct, there are 3 possible answers to the question whose assumption is correct. Neither assumption is correct, the one boxer assumption is correct, or the two boxer assumption is correct. We already know it's not possible for both to be correct because the two sets of assumptions contradict each other, so these are the only 3 possibilities. So what's the answer? Well, neither actually. The problem statement itself is vague enough that we don't really know what it means for the computer to be good at predicting our choice. For example, one interpretation could be, the computer being so good at predicting my choice means that no matter what it predicts, I'll probably end up choosing whatever it predicted. A different interpretation could be, the computer being good at predicting my choice means that no matter what I end up choosing, the computer will probably have predicted I would choose that. And yet another interpretation could be, the computer being good at predicting my choice means that my choice probably matches the computer's prediction. Under interpretation C, it's easy to show that we don't have enough information to determine which expected value is greater, because the one boxer and two boxer assumptions from earlier are both consistent with this interpretation. So the problem statement itself does not mathematically imply either set of assumptions. In fact, a completely different set of assumptions could be true. In this sense, if correct means mathematically implied by the problem statement, neither assumption is correct. An interesting observation, however, is that both the one boxer and two boxer assumptions are consistent with at least one interpretation of the problem statement. This means that neither can be excluded by looking at the problem statement alone. And since any person reaching a conclusion that one boxing is optimal or two boxing is optimal needs to exclude at least one of these two assumptions, that means that any person reaching a conclusion that one boxing or two boxing is optimal must be making assumptions beyond what was stated in the problem statement. Now, at this point, it might be tempting to say, fine, there's not enough information in the problem statement, but surely if we only allow making reasonable assumptions, then one boxing or two boxing will be optimal, right? Unfortunately, this is a very slippery slope to go down. What's reasonable for one person might not be reasonable for another. To some people, making any additional assumptions at all is unreasonable in itself. Also, in a world where we're willing to entertain the existence of a being from another planet with advanced technology and science, who's to say what's reasonable in the first place? Instead, I think we can focus on a more interesting question. Why does this all feel so confusing? I think one reason is that everyone that's reaching a conclusion that one boxing is optimal or that two boxing is optimal is making assumptions beyond what was stated in the problem statement. But these assumptions are so intuitive that it is very hard to see that we're making any assumptions at all, let alone that these assumptions are different. I think another reason this problem feels confusing is that as humans, we like to tell ourselves stories about how things happen. We want to see events play out over time and understand how they lead to a particular outcome. If you're a two-boxer, it can be very difficult to imagine a reasonable process in which one boxing is optimal. And if you're a one-boxer, it can be equally difficult to imagine a reasonable process in which two boxing is optimal. And as a fellow human, I completely understand that. So to make things more concrete, let's actually code up one example of each. As we already proved, both examples will necessarily make assumptions beyond what was stated in the original problem. But whether you agree with those assumptions or not, my hope is that you'll at least be able to see why someone else might find them intuitive. Let's start with the first example based on interpretation A. If the computer predicts you will choose both boxes, then you probably will end up picking both boxes. And if the computer predicts you will choose the mystery box, then you probably will end up picking the mystery box. Let's assume that the computer isn't perfect, so the probabilities are high, but not equal to 1. To make things concrete, let's plug in some values. Now, let's code this up and see which choice is optimal. First, let's create a general person class with a name attribute to hold the person's name, and let's add a p-mystery attribute set to none to hold the person's probability of choosing the mystery box. Then, let's add a choose method to simulate the person making a choice based on p-mystery. Now, let's create two example persons, John and Jane. John is a person that the computer predicted would choose the mystery box, and Jane is a person that the computer predicted would choose both boxes. Next, let's write a function to simulate a person playing the game after the computer has made its prediction. First, if the computer predicted the person would choose the mystery box, then it places $1 million inside. Otherwise, it leaves it empty. Next, let's set the person's probability of choosing the mystery box based on the computer's prediction. Then, the person makes their choice and collects their reward. Finally, let's have the function return the person's choice, the reward they received, and whether the computer's prediction was correct or not. Now, let's have John and Jane play the game 10,000 times and see what happens. Here are the results of John's first 3 games, and here are the results of Jane's first 3 games. If we look at all 10,000 games, the computer is correct in 99% of cases for John, and in 98% of cases for Jane, as expected. So the computer is highly accurate. But what's the optimal choice? Well, let's start with John. How much money did John receive when he chose the mystery box? $1 million on average? Not bad. What about when John chose both boxes? Okay, $1,000 more. So clearly the optimal choice for John is to choose both boxes. But what about Jane? Well, whenever Jane chose the mystery box, she made $0, and when she chose both boxes, she made $1,000. So clearly the optimal choice for Jane is to choose both boxes. In this scenario, choosing both boxes is optimal for John, Jane, and for everyone else. But now let's look at another example based on interpretation B. If you choose the mystery box, the computer probably predicted you would do that. And if you choose both boxes, the computer probably predicted you would do that. Now, let's create a template for a person. Like before, we'll give them an attribute to store their name and an attribute to store the probability that they choose the mystery box. Let's call it p-mystery, just like before. This time, however, let's add a new attribute called seed. Seed captures all the information in the world. The person's thoughts, their experiences, their personality, whether it's going to rain, and everything else in the universe that influences the person's choice. The idea is that if you knew p-mystery and the seed, you would have everything you needed to predict the person's choice perfectly. We'll update the choose method to depend on p-mystery and on the seed. And I'll add p-mystery as a kwarg to the init method to allow you to pick the person's p-mystery yourself. Now, let's write the function that the computer uses to make its prediction. When a person arrives, the computer retrieves their probability of choosing the mystery box and their seed. And then it uses that information to predict their choice perfectly. Now, let's create a function to simulate a person playing the game. First, the computer makes a prediction about what the person will choose, and then it uses that prediction to determine the contents of the mystery box. Next, the person makes their choice and collects their reward. Like before, let's have the function return the person's choice, the reward they received, and whether the computer's prediction was correct. Now, let's see what happens when people play the game. Let's create a dummy person called Peter, who has p-mystery equal to 0.5. And let's have Peter play the game 10,000 times. Here are the results of Peter's first 5 games. If we look at all 10,000 games, the computer is correct in 100% of cases for Peter. How much money did Peter make when he chose the mystery box? Okay, $1 million on average, not bad. But what about when he chose both boxes? Okay, only $1,000 on average, not so good. Clearly the optimal choice for Peter is to choose the mystery box. But what if we look at other people? Well, let's create a person called Sarah who has p-mystery equal to 0.99 and a person called Sam who has p-mystery equal to 0.01. If we have them both play the game 10,000 times, we see that the computer is still correct 100% of the time for both Sarah and Sam. But how much money did Sarah and Sam make when they chose the mystery box? $1 million on average each. And what about when they chose both boxes? Only $1,000 on average each. In this example, choosing the mystery box is optimal for Peter, Sarah, Sam, and anyone else. So what just happened? Well, we just watched two different worlds play out from beginning to end. In one world, choosing both boxes really was the optimal strategy, and in the other, choosing only the mystery box was the optimal strategy. The difference was in the assumptions we made about what it means for the computer to be very good at predicting your choice. In the first example, we used interpretation A and ended up constructing a scenario where the two-boxer assumption was correct and choosing both boxes was optimal. In the second example, we used interpretation B and ended up constructing a scenario where the one-boxer assumption was correct and choosing only the mystery box was optimal. Now, you don't have to agree with the interpretations I use in either example, but hopefully you can see why someone might find each of them reasonable, and after seeing both examples play out, maybe it's a little easier to understand how two reasonable people could arrive at different conclusions. So, after all of this, would you stick with your original choice, or did any of this change your mind?